Let's talk about here about the equipotentials and the direction of the electric field. What you see there is the two plates of a capacitor, one negative, one positive, and the electric field drawn with the red line, red arrows point from positive to negative. Now the equipotentials, we've discussed this before, inside the capacitor form planes that are parallel to the plates of the capacitor. So that means that the electric field lines and the equipotentials form 90 degrees. They're perpendicular to each other. This is for the case of a capacitor. The question is, are the equipotentials in general perpendicular to the electric field? Is this a general result that applies to any situation where there is charge and electric fields and potential? The answer is actually yes, it is a general result. It's not only applicable to the capacitor but to any situation. So how do you prove that? So start by looking at some equipotentials, some equipotential V sub A, V sub B, and V sub C. And let's say that we're going to move on the equipotential V sub B from an initial point to a final point, from I to F. The vector displacement is delta S. Now in that region of space there is an electric field, otherwise there wouldn't be potential electric lines or equipotentials. So that electric field between I and F points in a particular direction, and we're going to assume that F is so close to I that the electric field between them is constant. It doesn't change much when you go from I to F. There will be a general angle theta formed between the electric field and the equipotential. So the change in potential as you move from I to F, according to the equations that we've discussed before, is equal to the integral minus the integral of E dot ds. Since we're saying that this is a very short distance and the electric field does not change much, then we can take the electric field out of that integral, and the expression is minus E dot delta S. Both of those quantities are vectors. The dot product between two vectors is defined as the magnitude of one times the magnitude of the second vector times the cosine of the angle between the vectors. As you can see from the diagram, the angle between the delta S and E is theta. So the change in potential going from I to F is minus E delta S cosine of theta. Now we said that we're moving I and F are on an equipotential. So that means that there is no change in potential. The change in potential is zero because the potential at I is the same as the potential at F. If that's the case, then one of those three quantities in the equation minus E delta S cosine theta is going to have to be zero. Now the electric field cannot be zero.
I move from I to F some finite distance, so delta S is definitely not zero. So the only conclusion, the only possibility is that for this quantity to be zero, the cosine of the angle has to be equal to zero. No other way. So if the cosine of theta is zero, theta has only two choices. It's either 90 degrees or minus 90 degrees. Right? So what we're saying is that the electric field at that location, if this is the equipotential line, the electric field at that location, it's either going to be making a 90-degree angle with the equipotential or minus 90 degrees. So it either points that way or it points the other way, down. No other possibilities. Right? So the general result is that the electric field at some location in space is always going to be perpendicular to the equipotential that goes through that point in space. So once you've drawn, suppose that you already drew all the equipotentials in your problem, if you're asked about the direction of the electric field at some point in space, the direction you can be sure that will be perpendicular to that equipotential that crosses that point. But you still have two possibilities, right? If this is the equipotential, that you have, some potential value, whatever it is, how do you know if it's that, the electric field direction, or the other way? What would information you would need to determine whether it's one way or the other? Say it again. We don't need a source charge here, right? The electric field at some location in space is due to the sources. The electric potential at some point in space is due to the sources, right? And we talk about those electric field and electric potential independently of whether we bring a test charge or not, right? To do the calculation of those quantities, we use a test charge, but once we divide by the test charge, that quantity is gone. And we end up with a quantity that is independent of whether you bring test charges or not to space. You have to look at the neighborhood of that equipotential that you have there and see what happens to the potential in the neighborhood of that. So, there will be a equipotential just below that one and equipotential just above that one, right? If you know that the equipotential here is, say, higher than the equipotential here, the potential value here is higher than the potential value here, what does that tell you about the direction of the electric field then? We said that if you move downstream, your potential should be going down. Downstream means with the electric field, right? So if this, let's call this VA, this VB, this VC. If VA is bigger than VB, then you're going, if you move in the direction of the electric field, that is consistent with going from high potential towards low potential. You're going downhill, right? Imagine this line has been higher on the ground than VB, and then VC will be even lower. So you're going downhill. So that is the direction of the electric field, okay? But if you discover that VA is actually, this is VB, this is VA, and this is VC. If you, from the information given in the problem, if you know that VA is less than VB, right, then the downstream direction needs to be in the direction of the electric field, which will be, in that case, that. Going from VB down towards VA. Okay, your landscape there is has a slope going this way. A slope going towards VA.